Hi, my name's Dr. Hill, and my students like me to explain things in great detail. I was trying to explain to them how gases turn into liquids, and I had to stop myself talking about quantum mechanics. So this time I'm going to talk about molecules, and this is one molecule we're looking at. It's called ammonia, and there's the name spelling up there, ammonia, and it's made of 4 atoms: a nitrogen, represented by the letter N, that big purple atom, and hydrogen, 3 little H's off to the side. And the various pictures you see here, there are 4 pictures here. They're all models. The chemical formula for nitrogen is NH3. It's called the stoichiometric formula. Stoichiometric means it tells you how many of each element is in the molecule. So NH3, see the subscript 3? That tells you that there are 3 hydrogens. Now, models come in 3 types, or there's 3 ways to categorize them. There's the abstract model, which we're using at the moment, which consists of ideas: the idea of nitrogen, the idea of bonds of molecules. Then there's the physical models, which is the actual pictures or things that we build, and we use those to communicate with. But there's also the mathematical models. These are things which tell you numbers that we can test and measure. So the 3 model types come together, and we work them together to make hypotheses. So a hypothesis is a group of structured models. So I'll have my conceptual model. I may draw a physical model or make a physical model, and also have a mathematical model which will produce numbers. So the 3 of those together will produce a prediction. So I'll test the prediction with a hypothesis, or test the prediction generated by a hypothesis to measure the quality of my structure of models. Now, not all model systems are generated together to make a hypothesis. Some models are cut back and made simple so you can see. So the first model you see here is of nitrogen and the 3 hydrogens all oscillating. So this model is very good because it shows you that they're moving about the place. But in reality, there is not a particular color for each one. There's not the actual letter on the actual circular atom. The atoms don't actually look like that. But it's a very good model. It's a teaching model to show you that nitrogen is actually a little springy thing that moves about. Then up here we have the Lewis dot diagram. And again, it tells you there's nitrogen, and the lines indicate 2 electrons which are shared in covalent bond with the hydrogen, the 3 hydrogens. And we get a little bit more information here because there are 2 dots up here says that there are 2 unpaired electrons from the nitrogen. And those 2 dots cause those 3 hydrogens to be pushed down, as you can see. So that explains, it's also a teaching model, and it explains why the hydrogens are in 3 dimensions are pushed down. That's a 2-dimensional Lewis dot diagram. Here we have a 3-dimensional diagram just underneath, and it has some mathematical information, but they're not predictions, but it starts to show you things in 3 dimensions. So if the bond is to the rear, it's a set of dashes, and if it comes towards you, it's a triangle. If it's in the plane of the page, it's flat. So that's a way of producing a 3-dimensional model. Below is something which is quite more difficult to understand, and that's getting towards a quantum mechanical model. And those lone pair of electrons are actually this beautiful shape. So that shape of the electrons, and it's called a lone pair. So there's 2 electrons up there. You can't see the 2 individual ones because they're actually superimposed each other in space. They're not individual little electrons flying about the place, but they're a beautiful big cloud in quantum mechanics. So all of these things I want to explain a bit more And you can see, going from a simple school model to a slightly more complex model, I have to start talking about the idea of quantum mechanics. Before I move on, I want to give a few facts, common facts about ammonia, because my students really like to know lots of facts. So ammonia that you see there dissolves in water, and dissolved in water it makes basic floor cleaner. So if you get a floor cleaner, I think the commercial name is Handy Andy, and you open the bottle and you get your hand, don't smell it directly but waft the smell, you'll smell ammonia. Now ammonia is toxic and it's a stimulant, so it's been used when people have fainted to wake them up, and that's why it's called a smelling salt. It's also used in explosives, not as an explosive itself, but as a chemical which can be modified further by adding different things, removing a hydrogen and adding other groups to it to make a chemical. So many explosives have nitrogen in them, say like trinitrotoluene. It has several ammonia atoms around a benzene, that's TNT. The ammonia that you see here, if it comes out of the water and turns into a gas. So these molecules which you see are stationary, so a molecule is a combination of one or more atoms stuck together. This is not only a molecule, it is a compound because it is made of more than two different types of elements. It wouldn't be a compound if it was made purely of nitrogen or purely of hydrogen. That would be an elemental molecule. So normally these little things would fly around and bounce off the edges of containers as a gas. So there'll be many billions and millions of these in a gas bottle full of nitrogen. Here we come to the start of the talk, where I was going to begin before, and you can see the nitrogen up there which started it all off. But I now know that you want lots and lots of detail, so I began to explain it to you. Now let's begin quantum mechanics. Now everyone has heard of quantum mechanics, but what is quantum mechanics? Quantum mechanics is a conceptual model. So it's a group of ideas and thoughts brought together. It's also a very mathematical model, and you can see that certain pictures and models are called quantum models. So these pictures are very successful. So if you want to calculate anything or actually do anything in science, you have to really use quantum mechanics. The title here, Let's Begin Quantum Mechanics, means that this talk is going to be about how you can start to even begin to understand it, the very basic ideas. My name's Dr. Peter Hill. I'm a molecular physicist and I'm a teacher at Penrith High School in beautiful Australia. The word mechanics means a system of explanations of how things work. So quantum mechanics means an explanation of how things work based on the idea quantum, and we're going to start to really look at that word quantum. The title of this slide is Quantum Physics. It's all fuzzy. Now physics really is the study of nature, the laws of nature. So physics uses maths in this description of the laws of nature. It does experiments, but it also is the basic toolkit used by chemists. Now here is the basic statement in that if you've got a good model, one of the very first things you see about it is the idea that it's all fuzzy. Now I've said a few things here. It's very beautiful and it's also very logical. It's a very successful model. In fact, it's the model so far which has had no problems whatsoever. The picture off to the right here of a yellow going to green, blue and red gassy orb moving up and down is the picture of a single electron. It's not like the little electron you see in Homer Simpson going around an old style atom that was several hundred years or 100 years ago. It's actually a fuzzy ball, and you can see here it's being pushed around and changing shape, and what it's actually doing is it's absorbing light, and one way of looking at it is that it's holding light inside itself. And the top level here is called a atomic potential. This describes the force. This describes the force of a central proton in the center, which is positively charged, pulling that large cloud into itself. And so the force close to the center is greater, but further away it's much more gentle. You may see a curve like this, say in one of those coin grabbing surfaces where you put the coin and it rolls around. The red line refers to the energy or the excited level of the electron as it goes around, as it starts to absorb light. And down here, the little circulating arrow is referring to the electric field of the light coming in. And Q stands for the charge, and E is for the electric field as it spins around here at this angle. Little circles refer to something called quantum numbers. So what happens is that the actual quantum numbers change as the light comes in. It goes from one to the other. And this is very successful because it explains the shape of things that we see. Really basically everything, the color of light absorbed, the shape at which everything comes out. So this is why I say it's very logical. It does really describe everything you can think of. So why I enjoy quantum physics is it allows you to see more of nature, you see things and you really understand it more deeply. And so for me, that gives me great enjoyment, and I like to share it with people best I can. Now, for me, quantum physics didn't come easy, and it requires great patience to actually read through papers, understand a bit of maths, and realize that some of the things that you're told are not necessarily the most effective. And a lot of things you're told are by people who want to convince you that they understand things, but really don't, and they leave the room very quickly. What I think of them are a bit like snake oil salesmen. So back in the 1850s, there'd be people who would come around with not a very good product, wouldn't have any value to them. And it's typically called snake oil, so it had no effectiveness, but they would recommend it to you, swear by it, sell it to you, and then quickly move on. They didn't want to hang around and explain things. So a lot of people who tell you things about quantum mechanics, I have found over the time, don't hang around to explain things. When you ask questions, they just say, oh, that's good enough, it's good enough for school, and things like that. Now, one of the things you do find going around here is a lot of the words that are used in textbooks or by people are not necessarily well thought out. So I think of it a bit like a darkened room and you come across some furniture. Now, you don't know whether the furniture is there for a reason or someone's just left it there. So it takes a bit of time for you to get used to the darkened room and for your eyes to adjust and for you to think. And you have to be quite quiet, because if you run into chairs, you just hurt yourself. So you have to work out where things are. So this talk is to go in and talk about some of the basic words in quantum mechanics and try and set you on the right course so you can understand it. It's quite mesmerizing seeing that beautiful stuff, and with the computers you can move around in 3D. This is the atom, which is absorbing light. It's quite mesmerizing to see. You can see things in 3 dimensions, and it's really, really beautiful. So computers and virtual reality is a great way to experience quantum mechanics in a way that the people just a few years before could never do. The key word I want to really get into is the word quanta or quantized. So this is a word that people use interchangeably, but they really mean different things. And if you listen to one explanation, you can be led up the garden path, or you can be led down a way which will lead to confusion. So the word quantized is a very interesting thing. It refers to a particle, which might be an electron, a proton, a neutron, or a particle of light, which we say gets ejected from these atoms when you excite them. And these particles have quantum numbers. And so when it's quantized, it has a distinct set of quantum numbers, like a license plate. It might be 0, 1, 8 or 1, 4, 7. They would refer to different quantum numbers, and each one they would refer to a different time. But within those quantum numbers, it takes a little while to understand that there are really two types of quantum numbers associated with a particle. One is the fundamental quantum number, which is associated with how that actual particle is made. I'm going to use the word topology, which means the surface or shape. Another way of thinking of topology is sort of like a knot. So if you tie your shoelace, you can tie one crossover or a double crossover slip knot, but you can only tie knots in a certain strict number of ways that they cross over. So the fundamental part of one of these things refers to what they are, and also their angular, something called their angular momentum or spin. That's how they're knotted together in space. So that's will always travel with that particular particle. But there's another set of quantum numbers which are related to if you actually want to hold this particle, to actually hold it over a period of time, because it's moving, it folds over itself. There's only a certain number of ways it can knot itself or fold. And they're the shape quantum numbers. That's not the official name for them, but they refer to the particle in a system. So in an atom, an electron will have a spin quantum number and 3 other numbers which refer to how it dives into itself and folds as it goes inside that atom. And that's if an atom, but if you've got something large like a silicon chip, there will be literally thousands, well, 3 quantum numbers, but they'll be going up to the thousands. So you can have a very large quantum numbers there. So they are quantized, and they have quantum numbers which are just 1, 2, or 3. They're actual counting numbers which describes the allowed shape of what you see. Now, different from that is the idea of quanta. Now, quanta is a bit difficult because it's evolved in the time before quantum mechanics was written down in 1923, 26, around that time, by Schrödinger in a cafe. He was in a cafe and just wrote down, came to his head, the Schrödinger wave equation. So if you haven't picked it up so far, you're not going to see little dots, you'll actually see these beautiful waves. But the way that quanta came up was 50 years earlier, when people were looking at the concept of charge, and they said, oh, well, look, the charge is this much, but it comes down to little chunks of charge associated with a particle. And so an electron was thought that it does have the most basic unit of charge. So it's got a quanta, which is particularly 1 unit of charge. And so that was getting you to try and describe a particle. So before they didn't know electrons existed, and they were trying to work out whether they did. And they said, whatever these things are, they have a precise, there's more than one electron, and each electron has the same, exactly the same charge. So when I put them through a magnetic field, put a jet of electrons through a magnetic field, they all behave exactly the same because they have the same charge. So that was the first idea of what the word quanta is. So it's, in that case, quanta and quantized almost stuck together because they have a quantum number of 1 charge and they have a quanta of an electric charge. Now we come along to actually a very precise scientist called Planck, and this is a direct quote from his Nobel Prize speech. He had a different idea of quanta, and it's to do with probability. And this is his words exactly. They're called elementary regions. So a region, you think of an area. So he called that region an area. In his graph, he'd have 2 ideas and try to say you plot. So if you're plotting where a house is on a map, you draw it in a block. I know it's somewhere in that block. And he would say a quanta refers to the basic block size where an electron can exist, or he calls it a free room for action or probability. So it had a very much a probability idea. And so this is where he was working out that you just can't keep on going down in size. Eventually you don't have mechanical parts. So atoms don't have these tiny springs in them, and in fact atoms actually don't have tiny little electrons spinning around. So he's coming up with his idea of quantum. Then you have actually a third idea of quantum, which Einstein sort of had a hunch on, and he said that quanta refers to a packet of energy. So that light is a little packet. It's not a wave, it goes out as a packet, and it has a packet of energy. So quanta has got these 3 different origins for it, and really the first idea that electrons have a quanta of charge, that's sort of gone away. We now go with that's quantized, so it has a quantum number of 1 charge. Then we have this quantum mechanics going in really 2 different directions. So you've got the professional quantum physicists who go with Planck's formulation, and you have the people who want to teach quantum mechanics because it's very accessible, talking about the quanta of an object, you know, just how much of something is in an object. And that it's all the same. So like electrons all having the same charge, all blue light particles have the same amount of energy, around 4 something called electron volts of energy. This is a quick summary slide for quantized. That refers to particles and the properties of a particle, and the quantized means it can have a quantum number of integer or half integer, but for quanta it refers to the amount of a particular property. And there's 2 types of quanta. There's quanta associated directly with a quantum number, like angular momentum, or indirectly, like energy. Now let's cut our teeth on our first quantum particle, which is a photon, which is both quantized and has several quanta associated with us. Here we have the basics quantum mechanical equation everyone uses, and that's down here. So if you have a wavelength, of some light and you put it into this equation, it gives you the energy or voltage, the quantum voltage associated with that light. So if something's 620 nanometers, which is in the red, and you put it into this equation, it will tell you that the voltage associated with that particle, light particle, is 2 volts. That's 1240 divided by 620, which is 2. Now we've got some pictures here. Over here we've got these 2 atoms, and they're pictured as classical atoms with the tiny electron orbiting the nucleus, positive nucleus, and this electron goes from the outer shell to the inner shell, the left one, and emits a squiggly little red line, which is our photon, which is several wavelengths. But this is just an artistic impression. So the actual light doesn't wiggle up and down, it actually stresses the space in those directions, it creates an electric field in space, and then goes into another atom and causes it the electron to move. Now you've seen earlier on, it actually causes the electron to change shape. Now on the side here we have another picture which is interesting, but the light is not a spinning arrow moving around, and this is showing light which is going as a spiral. We would call this circularly polarized. It can be polarized, in this case in the clockwise direction, but it can also be anti-clockwise polarized. Now this arrow represents the strength of the electric field. So rather than see anything, if you have an electron, it just shows you the force on that electron. So it's a bit like an earthquake traveling through the place, and it's just like a wave. It's a force wave. So they're the pictures, but light obviously you can see, and it's not a squiggle, and it's not a corkscrew. It's actually a traveling force wave, electric force wave, and magnetic force wave. Now if we get down to light, it has a quantum mechanical property of spin. This is really fundamental idea. It's fortunate in light that spin corresponds to a readily observable phenomenon called polarization. So the spin can have a quantum number of plus or minus 1. I've got the slide back to front here. So the quantum number is plus or minus 1. It doesn't have a 0 because it's a massless particle. So if it was any other type of particle of this class, it would have a possible quantum number of 0, and therefore carries a quanta of angular momentum, which is given by this formula in the first line, h divided by 2 pi. H is a Planck's constant, so it's a very small number. It's an experimental number, a bit like pi or some sort of funny number, but it's very, very small. So light carries with it a bit of spin when it comes out of it. Now this means that when light is ejected, it is quantized. It can have plus or minus 1 in its spinning angular momentum, and it carries a quanta of h on 2 pi or minus h on 2 pi, and that's a value of, if you'd like, spin, similar to spinning a top, how much you would turn and spin a top. Now so that means that its angular momentum is of that first type with a quantum number. The second type, so this means that for light to be ejected, and it goes out as a photon, it means that the photon comes out of an atom and it has a certain number of wiggles times a certain and those wiggles are a certain height. So if you double the height, you say, for instance, half the number of wiggles. So that's sort of a fixed amount. So the more height, the more of it does an angular momentum kick per wiggle, or oscillation. We can have a lower oscillation and fewer, and lower height of oscillation and more wiggles. But the net effect is that any light comes out has to have the same spin. So it's quantized in spin, and it has a quanta of this angular momentum, any light that you put out. Now, if you look at the set number of wiggles and ask how much energy is there, the energy is proportional per wiggle to the frequency. So that's how quickly it wiggles. So if any piece of light has a quanta of energy associated with it, E equals HF, with F is the frequency. So if you multiply this tiny number h by the frequency, you'll get the energy in joules of an individual light photon. So individual light photons carry energy, but all photons of a particular wavelength or frequency or color, they all have the same quanta of energy, but they're not quantized. So every piece of light has a quantized amount of angular momentum. It gives a quanta of angular momentum because it's quantized, and because of that there's a fixed amount of wiggles at a certain height given out, and that fixed amount of wiggles times the frequency will give you the energy. So the energy is, there's a quantum of energy, however the energy is not quantized. Then we come to this next slide here, which is 9, which means HSC, 8 means quanta to quark, 1 means the first dot point area, 2 means you have to teach this to students, and 4th means the 4th point you have to teach to students. And it says, discuss Planck's contribution to the concept of quantized energy. Now, the problem here is that the energy, there are quanta of energy. The energy itself is not quantized. The energy itself is not determined by a quantum number. I'll just see if we can continue further on. To underline all of this, we really have to get different ideas. And we've got 4 maths concepts to sort of link up with the quantum mechanical concepts. Now, a continuous property, or something which is a continuum, will, no matter how much you focus on it, have a value. So all the lengths from 0 to 30 centimeters on this ruler here, no matter how much you focus on it, you'll still see a ruler there. So the value or the length there is a continuous quantity, but the length that you read out from arranging a certain number of nails is a discrete. It's at only one particular value. And the number of nails can be 1, 2, 3 or more. So that's a quantized number of nails. However, the length that you get of that nails is a quanta of the nails. So if I have a length made out of a quantum number of 3 nails, I get a length coming out, which is shown out here, and you can focus more and you get a line, or a line on the actual length here. Now, the really interesting part of quantum mechanics comes from when you look at that line a little bit more. Now, what happens is that in the case of position, it takes a while for that line to settle down. So the longer length of time you measure it, the more narrow that line becomes. So that line is not a mathematically discrete amount like 2.1, 0 straight or more. It's a range of values. So if you have an instrument which measures it, you'll see a fuzziness. So on the right, when you measure it for a very quick amount of time, it gets very fuzzy, and over time it gets thinner and thinner. Here's a picture here of the lines of photon energy produced with different colors. So the red is emitted with a quanta of energy, and so the red has a certain amount of energy. The blue here, this is for hydrogen. So these lines here represents the quantum numbers of electrons, but they're bound within an atom. So this is a captured electron, and it has additional quantum numbers associated for it being held in an atom. And above it, I have pictures of the nail, which if it comes at you quickly, or it's generated very quickly, the nail comes out very fuzzy, the actual position of it here, and in the space over here it's the energy of that nail. So the energy of the light. Coming back in summary, we have an interesting view on quanta and where it goes. So Helmholtz early on was a scientist, and he was looking at charge and used the word quanta for the amount of charge. And so now we don't tend to use that as much. We tend to look at the quantum number associated with charge. It's not such a big issue that an electron has a quanta of charge. Its quantum number of charge is 1. So we don't look at that as much. Planck, however, looked at quanta in terms of a fixed area in probability space. Now this is really interesting because we've been able to tweak this probability space, let the probability really roam in one dimension, in one axis. And so because it's a fixed area, it's reduced the variation in another. So we've been able to make these very highly accurate lasers using this quantum mechanics, which has created squeezed light, which has made ultra sensitive instruments, which has led to the discovery of gravity waves. So quantum mechanics has really snuck in there to save the day for us. And then finally we have the Einstein view of quanta of light. And he was able to work out that the light was in discrete packets of energy, but it's only afterwards that we've become confused and add the word quantized and quanta together. Thanks. Good evening.